So this is part two. This is actually part three, the third and final video for the Urysohn metrization theorem. And in this part, I'm going to go through step two of the theorem. And the proofs involved in this part are a little bit less original to the Urysohn metrization theorem, so I'm just going to be a little bit more brief regarding them. So we left off, we had a countable collection. We proved that there's a countable collection of continuous functions from x to this closed interval 0, 1, and it has these special properties that we went over. Now, in part two, we are going to use this collection to define a function from x to r omega. And this function is very simple to define. The function is defined, capital F of x is equal to f sub 1 of x, comma f sub 2 of x. And remember, we can do this, we can make these indices because the collection f of our functions, the function f, or the family f sub n, is a countable family. So that's why we're able to do that. Now, we need to prove that this function, in order to prove that f is an embedding, we need to prove that this function f is a homeomorphism onto its image, basically onto the subset of r omega, which f is mapping x onto. So these are all simple things to prove. What do we need to prove, first of all? So we need to prove that it is a bijective continuous function. And that is easily provable. We prove that it is injective. We prove that it's obviously surjective onto its image. And we prove that it's continuous. And the fact that it's continuous is a result from the chapter on continuous functions, that we have all these functions f1, f2, f3, they're all continuous functions. So now in the product topology of r omega, this function is also continuous, and that's just a result from the chapter of continuous functions. And the final part of the proof really is that f inverse is also a continuous function. And given the fact that f inverse is also a continuous function, the function f is a homeomorphism, and therefore the function f is an embedding of x into r omega. And that is what this whole proof has been about. We needed to embed our regular space x, which had a countable basis, into a metrizable space, which we chose as r omega in the product topology. And we have done this. And that concludes the proof of the Urysohn metrization theorem.